Welcome back. So the good news is that we are done with the complicated proofs from last week. So what we are going to do is to try to make things a bit more concrete and give particular examples of RKHS. And let us start with the simplest one. So the simplest one is also probably not the most exciting. This is the one which is related to what we call the linear kernel, which is simply the Euclidean inner product in RD. So as you may anticipate, the RKHS of the linear kernel is in fact the space of linear functions. You will see that the definition is quite related to the classical definition of duality that you may see in linear algebra classes. So let us first state the theorem. So indeed, the RKHS of the linear kernel, when the data lives in RD, is simply the set of linear functions. So what is a linear function here? It's a function which can be written as an inner product, okay? Where the inner product is parameterized by a vector W, which also lives in RD, such that we are going to write these linear functions as functions f parameterized by W. Okay, and basically fw, for us, it would mean the same thing as the vector w here. Okay. And of course, the inner product, which is natural here to use, is simply the one such that if you consider two functions, fw and fv, in this space H, which is simply RD, the corresponding inner product is simply the Euclidean inner product between W and V. And of course, the corresponding norm is simply the norm of W for any function that lives in this space. So now that's a theorem. So how do we prove it? So we prove it simply by looking at the definitions that we have introduced. So it's like a good time to look again at the definition of RKHS. And that's what we do first. I mean, there is a first thing to do, of course, which is to check that our space of function that we are describing is indeed a Hilbert space. So here, like I told you, it's related to the definition of the dual of RD, which is itself RD. So it's a Hilbert space because it's more or less, it's basically the same as the Euclidean space RD. So let us check the 2 points that are important that are in the definition of the RKHS. So first, what are the functions kw? Okay, the functions kw are simply the functions that associate x to w transpose x. So given the definition, indeed, H contains all of these functions for every w in x. Then the other question is that, well, for every x in RD, every data point in RD, and every function fw in H, do we have the reproducing property? And indeed, we have it simply by definition. Fw of x is defined as the inner product between w and x, which is also the inner product between fw and the function kx, where here you simply change the notation here between w and x. So we have all of the definition we want, and thus H is the RKHS of the linear kernel. And remember that we said last time that the RKHS for a specific kernel is unique. Okay, so we are good. But of course, finding out which RKHS is associated to a kernel, it's not always as easy. And we are going to first see an example with the polynomial kernel of degree 2, which is simply defined as taking the square of the inner product. So typically, more generally, I should say that a polynomial kernel of degree 2 is obtained by allowing to have a small intercept before taking the square. Here, for simplicity in this slide, we simply consider the inner product x times y in RD, and we take the square. When we say find the RKHS of the polynomial kernel, of course, there is a first question to ask, which is, well, is it a positive definite kernel? Because if it is not, there is no RKHS associated to it. We have seen that RKHS and positive definiteness were the concepts that were linked together. That's what we did last time. So I will give you a few tricks to characterize the RKHS of a positive definite kernel. It doesn't mean that this is a recipe that works all the time. It means that if you can follow these steps for different kernels, sometimes it is useful to find out which RKHS we are considering. So the first trick, it consists of rewriting our kernel function k of xy as an inner product, as a Euclidean inner product. Because remember that if you can do that, if you can write k of xy is equal to some inner product between phi of x and phi of y for some mapping phi, then you have not necessarily characterized the RKHS. What you have done is that you have shown that the kernel is positive definite, okay, such that we can talk about the RKHS. So we are going to do this, and for that we will observe that our squared inner product k of xy is in fact equal, if I jump to the last line, to the Frobenius inner product between two matrices. So what is the Frobenius inner product? It's actually the natural extension, let's say, of the Euclidean inner product to matrices that consist of taking two matrices as input, seeing these matrices as vectors. You would simply vectorize and forget about the matrix structure and take the resulting inner product, Euclidean inner product. That's something that you can do all the time. If you know how to manipulate NumPy or PyTorch, you often, remove some dimension, vectorize. That's something that which is easy to implement. So in math, it's simply called the Frobenius inner product. It's associated to the Frobenius norm for matrices, where the square of the Frobenius norm is simply the sum of the square of the entries of the matrix. The same as for a vector, except that we deal here with matrices. Now it turns out, and we will see why, that this square inner product, x transpose y squared, is equal to the inner product in Frobenius norm between two matrices, two rank 1 matrices, which are x transpose and y transpose. So why is that? It's simply because of a very basic property of the trace operator. So it may look a bit weird, but we will see that by following a few tricks, we'll get to this result. So the first thing we do is that we write x transpose y squared is equal to x transpose y times x transpose y. So not the most exciting part of the proof. And then we take the trace of it. So the trace of a scalar value is the same scalar value. It's simply the identity. It looks like it doesn't make sense. So let us work a bit more. What we first do is that for our first inner product x transpose y, we use the symmetry and write it as y transpose x, the scalar, times x transpose y. And here we use a property of the trace, which is that if the dimensions allows you to do that, the trace of A times B, where A and B are two matrices, is equal to the trace of B times A. So if you are not convinced by that, really just write the definition of the trace. And of course, you take the trace of a square matrix, which is always the case here. And just check that this property is true. So what we do here is that we, instead of seeing that as the product of two scalars, what we are going to see that as the product between the vector y transpose, the square matrix x transpose, and the vector y. So it's just, again, a matter of playing with the definitions of matrix multiplication, such that you get this result. And we're going to move our vector y transpose on the right. So that gives us the trace of the product of two matrices, two square matrices, x transpose, and y transpose. And it turns out that, again, you need to check the definition of the trace of the product of two matrices, such that you are going to see that the trace of A times B, if A and B are two symmetric matrices, will be simply the sum of the AIG, BIG. Basically, the natural extension of the Euclidean inner product after vectorizing the two matrices. In other words, this is simply the definition of the Frobenius inner product. So you see that here all we did was simply using a basic property of the trace operator plus playing with the notations, nothing else, such that at the end, what we have is that we have that this kernel K, xy, can be written as an inner product between a quantity that depends only on x, you may call that phi of x, and here a quantity that depends only on y, and you may call that phi of y. So you have written your kernel in a way that allows you to say that it is positive definite. And that's a good news for you already, because you can now talk about the RKHS. So what is the second step? So we have proven positive definiteness, and we have a way to write our kernel as an inner product. Okay, we were going to provide a candidate RKHS. So what is a candidate RKHS? It will be simply a Hilbert space that we believe may be the RKHS. And then we are going to prove that indeed it was the RKHS. So how do we do that? We use the first property of the RKHS, which is that we know that the RKHS contains the functions kx. Remember that for all x, it contains the functions kx. And given a collection of points x1 to xn, for any collection of points, it should contain all of the linear combinations of this kxi. So in other words, we know that for every x, every collection of points, for every collection of points x1 to xn, and any set of scalar values a1 to an, we know that the RKHS H necessarily contain the functions of the form f of x that are a linear combination of the functions kxi that can be written as the sum over I of the ai k of xix. Now here is where it becomes useful to do what we did in the previous slide, which is to see our kernel as an inner product. So we do it. And now that we have done it, we can use the bilinearity of the inner product and simply group the sum and the ai inside the inner product such that we know that H contains necessarily, it may contain other functions, but at least we know it contains the functions that can be written as f of x and that can be written as an inner product between xx transpose and some linear combinations of the ai xi transpose. Now it turns out that if you remember your linear algebra classes, that any symmetric matrix in R d times d can be decomposed as a sum of rank 1 terms. So it can be decomposed as the sum of ai xi transpose for some scalar values ai and for some vectors xi. So if you are not convinced by that, you check in your linear algebra classes simply the part about eigenvalue decompositions. It will give you this sort of decompositions. So that's a good news because it means that at least we know that the RKHS H contains at least all of the functions of the form f of x that can be written as an inner product between S and x transpose. For any symmetric matrix S. So if we simply use again the definition of the Frobenius inner product in terms of the trace, and that we put x transpose, which is on the right here on the left, we can also check that this quantity is equal to the scalar value, of course, which can be written as x transpose times S times x, where S is a symmetric matrix. So it means that we are going to simply propose some Hilbert space, which is let's say the set of functions of this form which are parameterized by the set of symmetric matrices. So this is indeed a Hilbert space. It's pretty easy to see when you choose the following inner product, which is that if you consider two functions in this set fs1 and fs2, you simply consider the Frobenius inner product between s1 and s2. And that's a good news because we have what we have. We have a candidate RKHS. We have basically a Hilbert space that has an inner product that contains all of the functions kxi. Basically, we are going to check. Well, first we check that the candidate space is a Hilbert space. Basically, we build it as a Hilbert space. So in that case, it's very easy. It's a space H, which is isomorphic to a Euclidean space, which is the set of symmetric matrices. Sometimes things are much more complicated, but in that case, the fact that this candidate set is a Hilbert space is simple. Now we check that it is the RKHS by looking again at the two properties. So again, that's a good time to remember the definition of the RKHS. H contains all of the functions kx for any vector x, which are simply the functions defined as the function that gives k of xt given a vector t, which we have shown can be written as an inner product between x transpose and tt transpose. Okay. So indeed, it has the shape of the functions that we have defined in the previous slide. Now, for all function fs in this space H and vector x in the input space, we are going to check that the reproducing property holds. Indeed, this is the case. Fs of x is equal to the inner product between s and x transpose. X transpose, this is nothing else that it can be simply, so this inner product here, by definition of the inner product in the previous slide, is also the inner product between fs and fx transpose. And this quantity here, this is simply kx. So we are good. We have the definition of the RKHS, and we have shown that if you choose the polynomial kernel of degree 2, what we are doing is implicitly defining a Hilbert space of function, which is the RKHS, which is the set of quadratic functions parameterized by a symmetric matrix S. Okay, so it looks pretty natural, and you see that the proof is not that complicated after you use the trick that allows you to represent your kernel as an inner product with a specific mapping. Basically, after you do that, you have done half of the job. So there is an important remark here, which is that all points x in original set are mapped to a rank 1 matrix XX transpose, which is this function kx that we call fxx transpose in the definition of this Hilbert space. But the question is, the remark is that most of the points in H do not admit a pre-image. What is a pre-image? A pre-image is, given a function in the RKHS, a pre-image would be a vector x such that this function can be written as kx. So the answer to this is simply that H does not only contain functions like this, it also contains all linear combinations of such functions. So it may look a bit simple, but this is important to take this is one of the important concepts in RKHS, is that even if you know what is the mapping phi of x that represents your data point in H, so here basically we take a vector x in the input space, we are going to represent it in the RKHS as these quadratic functions parameterized by x transpose. But we know that we are going to map the points basically to rank 1 matrices, but H contains much more than rank 1 matrices. It contains all quadratic functions parameterized by a symmetric function. Okay. And then there is an exercise, which we are not going to do, is what is the RKHS of the general polynomial kernel. So we simply replace 2 by an exponent p, and you can try to see if you can work your way to prove what is the RKHS. And you can start with p equals 3, for example, and then move to higher dimensions. Okay, now there are a few results that I want to present that are very useful to build positive definite kernels, because we are not going to go very far if we limit ourselves to the linear kernel, the quadratic kernel, I mean the polynomial kernel of degree 2. We have not even shown so far that the Gaussian kernel is positive definite, even so I gave it as example before, because this is one of the very classical kernel in the literature. So to do that and build a collection of kernels that we are going to manipulate in the rest of the lectures, we are going to look at the first simple theorem. And it's a theorem which is in fact pretty simple, but we call it a theorem simply because it has important consequences. So it turns out that the following result tells us that if you have two kernels K1 and K2 that are positive definite, then if you sum the two kernels, you get also a positive definite kernel. And the proof is pretty simple. It's, let's say this is left as an exercise. Similarly, if you multiply a kernel K1 by a non-negative quantity C, you get also a positive definite kernel. So this is also good news. And there is also this result which is much more interesting, because it is the one which is not completely trivial here, which is that if you take two kernels, if you take the product of two kernels, you get a positive definite kernel. You have seen that in a specific case, by the way. If you take the linear kernel, you multiply it by the linear kernel, you get the polynomial kernel of degree 2, such that we have shown one example where this was true. So in the next slide, I will go very fast. I will simply give you the idea of the proof, which is the same as the one we did to prove that the polynomial kernel of degree 2 was positive definite. One remark here, which is important to make, because sometimes things can be very confusing when you start discovering this literature about kernels, is that here we consider the product between two functions, meaning the element-wise product. If you have two kernel matrices, we are not talking here about matrix multiplication. We are talking about point-wise, element-wise multiplication, meaning that here for two input data points x and y, the corresponding quantity here will be k1 of xy times k2 of xy, which is not matrix multiplication. So we are going to see that it gives you a positive definite kernel. And finally, the last result is simply a limit result, which is in fact very easy to show, that if you get a collection, a sequence of positive definite kernels ki, if this quantity converges pointwisely to a function k, meaning that for every pairs x and y, the sequence ki of xy converges to a limit that we are going to call k of x prime here, because I used x prime instead of y, then k is also positive definite. So I must admit that if you are thinking about using kernel methods in practice using Python, let's say, this may look like simply an academic exercise. And indeed, this is purely an academic exercise, but it's actually very useful to prove that many of the kernels that we are going to manipulate are positive definite. So let us maybe start, before I give you examples on how to use that, let us simply start with this result here. The product, the fact that the product of K1 times K2 is positive definite. So what we do here is that we consider n points in the input space and the corresponding kernel matrices K1 and K2 that are positive semi-definite. So at this point, to prove that the product K1 times K2, which is the element-wise product, is positive definite, either you have seen this result already in your linear algebra classes, it's called a Schur lemma, and there are many Schur lemmas, but this is one of them. Otherwise, we can simply prove it. To prove it, we are going to manipulate the trace operator. So since these matrices K1 and K2 are positive semi-definite, you should know that they admit factorizations. K1 can be written as X transpose X for some matrix X, and K2 can be written as Y transpose Y for some other matrix Y. Now, if we consider the entry Kij of our kernel matrix, which is the product of the corresponding entries in K1 and K2, we can simply write, so we can write every entry here as a linear product between two columns of X. Here we can write it as a linear product between two columns of Y. We have a scalar values. You can take the trace of it. Then you can do the same as for the polynomial kernel. We simply use the symmetry of the first linear product. We move the Y here on the right. And at the end, what we have is we can rewrite this as the Frobenius inner product between two rank 1 matrices, Xi, Yi transpose. So this part only depends on the index I. This is Xj, Yj transpose. It only depends on the index J, such that we can write this as some Euclidean inner product between two vectors, Z1 and Zj. In other words, what we have shown is that K also admits a factorization as some matrix as Z transpose times Z, where Z is a matrix. And thus, it is positive semi-definite. And we have shown that this kernel K is also a positive definite kernel. Okay, now let us use it and look at the first example. First example is that, well, another result is that if K is a kernel, then if you take the exponential of this kernel, this is a kernel 2. Here, I'm not talking about the exponential of a matrix. Here, this is simply the exponential function applied to another function. Okay. And the proof, we use the previous result. We simply use the definition of the exponential function, which is the limit when n goes to infinity of this sum here. And remember now that what we have shown is that if K is a positive definite kernel, if you multiply it by another positive definite kernel, you get a positive definite kernel. So that will means that this kernel here, if you take the exponent I, is a positive definite kernel. If you rescale it by a non-negative value, this also gives you a positive definite kernel. Now, if you take a sum of positive definite kernel, you get also a positive definite kernel here. And when you take the limit, you get also a positive definite kernel, such that we have shown that the exponential kernel, the exponential of a kernel function, is positive definite. Now, we could do that for many other kernels, but I'm going to keep that for the discussion session, in fact. And there will be a small quiz, and try to see if, given what we have done so far, you are able to tell me which of these kernel functions are positive definite kernels. We have functions sometimes that simply take values on some open interval. Sometimes we have kernels for natural integers, sometimes for only non-negative values. So the input set is sometimes different. We see that we have trigonometric functions. We have here some min and max functions, here the mean over the max. Here we have what we call the Gaussian kernel, simply for real values. So you should know already that this is a positive definite kernel. Now the question for you is, what is the simplest proof you can find to tell me that this is a positive definite kernel? Quite interestingly, there are kernels at the bottom. Some of them are positive definite, some of them are not. So what is the GCD? It's the greatest common divisors between two numbers. This is the least common multiples. So it may be, it looks very different from everything we have seen done so far, but these are just interesting examples that show that, well, in theory, we should be able to do machine learning on the set of natural integers by using these things. But I must say that I have never seen that used in any practical applications. It's just a quite interesting case of positive definite kernel. I will simply give you a hint. This one here, the GCD is positive definite, LCM is not, but GCD over LCM is positive definite. And if you manage to find the proof of this, then it means you have well understood everything we did so far. Okay, and the last thing I want to present before we stop today is this part about smoothness functional. What it means is that simply I want to give you an intuition about the fact that the RKHS norm encourages some smoothness. So there is one slide. When we want to get some intuition, what we do is that we often first by looking at what happens with the simplest possible case, which is the linear kernel. And here we consider the linear kernel. Remember now that the functions in the RKHS are parameterized by some vector W. They can be written as W transpose X. These are linear functions. And the norm in the RKHS is the norm of W. In 1D, if we plot the three different functions for different values of W, meaning for different norms, what we see is that, well, the slope of the function is related to its norm. So meaning that if you have a large norm, you have a function with a higher slope, which is less smooth in some sense. It's a bit weird to talk about smoothness here for linear functions, but it's a bit less smooth because it can produce larger variations, meaning it's a bit more unstable. If you change a bit x on this axis, it will change more f of x. And this intuition can be characterized by the following inequality in the most general case, which is actually the most important message of this part of the class. This is something which is really a key to kernel methods, which is that this RKHS norm is a quantity which is very natural to use to induce smoothness, such that it's a very natural quantity to use as a regularization function. So the way we do this is that we consider a function f, two data points x and x prime, and we will try to control the deviation f of x minus f of x prime. What we want to do is to simply understand what are the quantities that can make these things close to each other or far from each other. And what we do when we deal with kernel methods is that we always use the reproducing property, because you will see it will be very useful to answer this precise question. So we use the reproducing property. F of x is simply the inner product between f and kx. And this is simply the inner product between f and kx prime. So we linearize these functions in this higher dimensional space, which is the RKHS. We use the bilinearity of the inner product. And since we have an inner product, we do something that we always do when we prove any result about RKHS, which is that we use Cauchy-Schwarz inequality. So Cauchy-Schwarz inequality tells us that this can be controlled by the product of two terms. One of them is the norm of f in the RKHS. So it's a quantity that only depends on f. It does not depend on x and x prime. And this other quantity is simply the norm of kx minus kx prime, which is the distance between x and x prime after mapping your data in the RKHS. And this is something which is independent of f. So it's a property of the data. Here, this is a property of the model. So you see that we are decoupling data representation and distance induced by the kernel that we call dk, and the part that depends only on the model, f, that you are going typically to learn on training data. So this equality tells us that if you have x and x prime that are close to each other in terms of data, meaning that this quantity is small, sorry. If you want f of x to be close to f of x prime, you need to have a small norm. So that means that if you want to have a function with small variations, you need to have a small norm. And this is why this quantity will be used as a regularization function, and this is why the RKHS norm is related to a concept of smoothness. And you will see in other classes that there are particular RKHS where this concept of smoothness is related to concept of smoothness that appear in many other contexts. So again, this is the important message of the day. So really spend some time on it if you don't get it. Small norm leads to slow variations of the functions f. And I guess that would be here. So, okay, a last summary before we stop today. So the summary is that positive definite kernels can be seen as inner products after embedding the data space in some Hilbert space, which is the RKHS. A realization of this embedding is the RKHS, which is valid without making any assumption on the space X nor on the kernel function, except a positive definiteness, of course. It turns out that this RKHS is a space of functions. So this is the part which is a bit abstract when you first study kernel functions, but in fact, it becomes simpler and simpler after doing exercises on it. And the norm of a function in the RKHS is related to its smoothness with respect to a distance induced by the kernel function. So induced by some geometry, if you want. So next, what we are going to do next week is to see some applications of kernels and RKHS. So we are going to go from the math part to the more practical part. So we are still going to do a bit of statistics, a bit of math, but we are going to get closer to concrete implementations and concrete algorithms. And later we'll see, we'll come back to the question of which kernel to choose. And can we maybe design a specific kernel for a problem? Okay, that's it for today, and see you next week.